Hello, you're welcome back. All right, so we're still on refraction of light. So now in this part of the video, we'll be looking at the refraction in a thin lens. Okay. Now, what is a lens? A lens is simply a transparent body, usually made up of glass. Now, it has a regular curved surface. So, a transparent body that's usually made up of glass, okay, then having a curved surface. Now it's either the surface is curved inward or the surface is curved outward. All right, that actually gives us two types of lens. Okay, let me sketch that. Okay, so when it is curved outward, okay, that simply means that if the lens if the middle part of the lens is thicker, much thicker than the edges, then such lens is known as a convex lens that is curved outward. Okay, so if the lens is curved outward this side, where the middle is thicker than the edges, is called a convex lens. So this is a convex lens. Now it happens that a convex lens, okay, is converging in nature. It's also known as a convergent lens. Now already you know why it is called a convex lens. It is called a convex lens. Why? Because the reflecting surface or the refracted surface, a lens have refracted surface. Why? Because a lens only refract light. It only changes the direction of light. It doesn't reflect it. Okay. Now the refracted surface of the lens, okay, is curved outward. That means the midpoint, the middle part of the lens is actually is thicker than the edge. Okay, now if I should now draw a line passing through the center, of course you know very well that these axes, I call this axis my principal axis. Okay, now the center of the lens, okay, unlike the center of the mirror that we call pole, the center of my lens is called the optical center. I'll use C to represent it, optical center. All right, now why is this lens called a converging lens? Why is the convex lens also known as a convergent lens? It's called convergent lens because the parallel rays of light that passes through the lens, okay, all the parallel rays of light that passes through the lens, immediately they actually passes through, they will refract. Remember, a lens actually what it does is refract light. It's a glass, okay. It actually changes the direction of the light. So all these parallel rays that passes through the lens will actually undergo refraction. But as they undergo refraction, okay, all of them will converge at a common point known as the principal focus of the lens. So a lens also have what is known as principal focus. So that is the reason why a convex lens is also known as a converging lens. Why? Because all these rays of light actually converge at the principal focus. All right. Now don't forget that the same terms that we use in illustrating a curved mirror is what we also use for um, a lens. Okay. So now we have the principal focus. Now the only difference is that for a curved mirror have reflected surface. That means it's only one part of the mirror that actually reflects. But here in the lens we don't have reflecting surface, but rather we have refracting surfaces of the lens, which is either side. Okay, that means either side rays, any side that the ray of light actually passes through the lens, it will actually refract, okay, change direction and actually come out from the other side. So if I have the principal focus at this side, also I will also have principal focus at this side. Both side of the lens, okay, has principal focus. Then of course 2 times After the principal focus, I have 2 times the principal focus, 2f. Here too I have 2f. Okay, now this 2f is actually equivalent to the center of curvature of a mirror, so please take note of that. And of course the c here, okay, is what we call the optical center, which of course is equivalent to the pole in a mirror, called the optical center. This line here, you know very well that are my principal axis. Okay, so now that simply means that a lens will also form images the same way a curved mirror does. At different point of the, I place the object in front of the lens. Okay, then the image will have different characteristics. So that is why a lens, the lens formula or lens equation is also similar to mirror equation. Okay, so lens equation. Okay, before actually we look at lens equation, I've only talked about but let me take this out first. This is the one type of a lens, convex lens. Then the other type is actually the concave lens. Concave. So it's concave, or this time around is concave or divergent. Divergent lens. So for a concave lens, then you discover that a concave lens is rather thick at the edges than the center. Okay, it's very thin in the center but thick at the edges. Then why is it called divergent? Okay, of course you know why it's called divergent. Let me still draw my principal axis. Okay, having drawn my principal axis, so of course you know very well that it's divergent because the parallel rays of light that actually passes through the mirror, yes, they will actually undergo refraction, but that refraction will actually lead to divergence. They will move away from each other, as you can see. But if you trace the ray, okay, backward virtually, of course if you take it backward, the ray that just refracted, okay, then if you still trace it backward, discover that it will still meet at a common point. Okay, so just a common point, still the principal focus. So that means for a concave lens is divergent. All right, and of course the focal length or the principal focus is always virtual. Anyway, we'll talk about that later. So that's the difference between a concave and of course a convex lens. So now we'll now talk about the lens equation. So as I said, the nature of the image formed by a lens, okay, depend on the position of the object and of course the focal length of the lens. So that's exactly what you're going to, okay, represent in lens equation. So lens equation still remains, it's still the same equation that we use for that of mirror. Okay, that's 1 all over f is equal to 1 all over u, then plus 1 all over v. Focal length, object distance, image distance. Okay, and of course you also know that the formula will still change. A situation where the image is virtual. Okay, so that means the position of the object determines the nature of the image, whether it's virtual or not. So that means the same position when u is less than When you use less than f, okay, you know very well that at that point we'll have a virtual image. So the same characteristics I'm looking at, the same characteristics that we studied when we studied concave mirror is what we have for convex. Okay, so convex lens will have the same characteristics with that of a concave mirror, the same characteristics. So when the object is less than the principal focus, then the image is virtual. All right, and of course virtual, erect, magnified, okay. And of course you know very well that when you now bring the object to f, you still have a image form at infinity. So the same properties that we studied when we treated a curved mirror, okay, specifically concave mirror. That's what you get here. Okay, so now we will definitely I might want to actually study them one after the other, but I'm interested in solving question based on the mirror, the lens formula. Okay, all right. Okay, so now let's just walk through some question. So let's look at a concave lens, convex lens, please pardon me, convex lens of focal length. Focal length 10 cm. Okay, if an object is placed twenty cm from the lens, what is the image distance? Okay, solution. Here we go. The focal length of the lens is 10 cm. The object is placed at 20 cm. So we're looking for the image distance. Okay, from what we see here, seeing that the object is greater than the focal length, that means the image is real. So we apply the formula of 1 all over f equal to 1 all over u, then plus 1 all over v. So that's going to be 1 all over 10 equal to 1 all over 20 minus 1 plus, please pardon me, plus 1 over v. So making 1 over v the subject, that's going to be equal to 1 over 10 minus 1 over 20. Of course, the LCM is 20. LCM of the denominator, 20 divided by 10, that is 2. 2 times 1 is 2. 20 divided by 20, that is 1. 1 times 1 is 1. So I'm having 1 over v to be equal to 2 minus 1, that's 1. 1 over 20. So I have to find the reciprocal, okay? So v now is going to be equal to 20 cm. So my image distance is 20 cm. So in case you want to find the magnification, remember magnification is image distance all over object distance. Image distance is 20 cm. Object distance is 20 cm, which of course is 1:1. That means the image and the object, they are of the same size. Okay, and of course you discover that comparing it to what I actually talked about before, all right, when we discuss mirror. Okay, this particular object is placed 20 cm, that is 2 times. That means the object is placed at 2 times the principal focus. And if you compare this to that of a mirror, 2 times the principal focus is actually the same as the center of curvature. And when we actually treated mirror, we say that whenever an object is placed at the center of curvature, the image will be formed as center of curvature, and of course the image will be of the same size with the object. Okay, so that is just that. All right, so we're going to look at some other questions. Okay, uh in the next video. Right, see you in the next video. Thank you.